Thank you very much for giving me the opportunity to talk about this instrument here. I'm Mahmouda Sultana from the Planetary Environments Lab at NASA Goddard. My focus is on planetary environments and in situ chemical analysis. I'm the principal investigator of several instrument and mission concept development efforts at Goddard. And today I would like to talk to you about one of those instrument concepts, especially for measuring the volatiles released from the lunar lander. Can you move to the next slide? I can still see slide from the previous presenter.
Oh, that's unfortunate. I think there's a little bit of a lag. I'm sorry. I'm on site at Goddard, and sometimes the internet's a little slow.
I can see her slides.
We
okay.
see the one that says impact of the lander plume.
Okay. Yeah. Great. Next slide, please. So the delay might be at my end, which is unfortunate because I don't know which slide you guys are able to see.
We're on exhaust plumes from the lander.
Okay, great. Let me open this at my end, and I'm just going to follow along separately. Sorry about that. So we heard quite a bit about the importance of measuring lunar volatiles, especially the indigenous volatiles earlier today and also yesterday. So I'm going to go over this a little bit quickly, but lunar volatiles can give us a really good insight into the origin and evolution of our solar system, especially in terms of the volatiles that were delivered from various sources, including comets, asteroids, solar wind interactions, and also interior outgassing. While the Artemis and CLIPS program provide an unprecedented opportunity to... Can you guys hear me?
I can hear you now.
Okay.
Yes, we can hear you.
Okay, great. While the Artemis program and the CLIPS program provide an unprecedented opportunity to study the moon, any landing under these programs will also release a large amount of volatiles, as we have learned, that are not indigenous volatiles. And these volatiles, some fraction of them can get transported across the lunar surface and get trapped at cold traps, affecting any future measurements of indigenous volatiles. So while I agree with Noah that the PSI presents us a great opportunity to learn more, but we also have to kind of understand how the lander volatiles might affect the indigenous volatiles on the moon. So we are targeting the Artemis Science Objective 2F to understand the impact of exploration on lunar volatiles across the surface. Next slide, please. And please let me know when you are able to see the next slide.
I'm on the next slide, motivation, water release from the lander.
Great. So this schematic here kind of shows how water particularly can get transported across the lunar surface, and based on different studies, about 10 to 20% of that released water can get trapped in cold traps. So once water is released from the lander, a significant fraction of it will interact with the regolith, will absorb to the lunar regolith, and come off over time. And now the exact interaction can depend on the temperature, the location, the chemistry of the regolith. Next slide, please.
I'm on the next slide.
So there are different landers that might get awarded under the CLIPS program. However, looking at the exhaust composition of these different landers, we see that there are some common species, especially water, carbon dioxide, and carbon monoxide is common to different types of fuels used. Particularly, water seems to be the one of the most consequential component of the exhaust plume, both in terms of the amount as well as the lingering interactions it will have with the lunar regolith. We saw from Daniel Clemens' presentation that carbon dioxide has less amount, a shorter residence time. So we may not have substantial amount of carbon dioxide and carbon monoxide after, let's say, 24 hours. But water, some amount of water will be lingering around for a longer period of time. So we target water vapor with this particular instrument, but we are very much open to suggestions from this community about what other species might be interesting. Daniel also mentioned that there are microtraps where some amount of carbon dioxide might be present even after 24 hours. So that is something we're looking at as well. Next slide, please.
On the next slide.
So now I would like to tell you about the instrument we are looking to use to make in situ measurements. There have been significant modeling effort into looking at the volatiles that might be released from the lander and how they interact with the regolith. However, we don't really have a lot of in situ measurements. A lot of those modeling efforts use assumptions like adsorption energies and desorption energies and so on. But we really need some in situ measurement data in order to validate a lot of those assumptions and understand what's actually happening. So Multifunctional Nanosensor Platform is a highly compact, small, low power, simple and sensitive instrument that we are developing at Goddard. It's an in situ chemical analysis instrument, has a suite of environmental sensors to detect gases and volatiles. It also has a temperature sensor, microheaters, and so on for temperature control. One of the ways we keep this instrument really small and compact is by taking advantage of a number of cutting-edge technologies. We use nanomaterial-based sensors that allows us to achieve high sensitivity. Yet by printing them on a small substrate, we are able to keep the footprint really small. Next slide, please. Given the limited time, I'm not going to be able to go into the details, but this is supposed to be just an introduction. If you have questions or thoughts, please feel free to reach out to me. This slide showing the instrument block diagram is meant to illustrate how simple this instrument really is. We have very few components and very little room for complexity. So that's one of the big advantages of this instrument. Next slide, please. I'm not going to go into the details, but we are using a number of automated printing techniques, which allows us to achieve quite high reproducibility and yield. Next slide, please. Here you can see a picture of a completely standalone instrument on the left. I was able to do a field demonstration of this completely standalone instrument in Alaska last year. On the right, you can see some numbers in terms of instrument performance and what we expect for water concentration from these plumes. And we have quite a good sensitivity to be able to measure the plumes expected. Next slide, please. This is a possible mission concept where we mount the instrument on a rover. Given the small footprint of the instrument, we should be able to fit in a small rover which can rove around, and we can take measurements as a function of the distance from the landing site, as well as over time, and as a function of perhaps temperature. We can look at some of the shadowed regions, which might be difficult to do from the lander itself. But in the future, we can also send a network of these instruments on rover and map out the concentration of volatiles in an autonomous fashion. The small footprint really allows us to send a number of these in a relatively low-cost mission. Next slide, please. We are doing extensive modeling to understand the amount of concentration of these volatiles expected, and also guide some of the instrument design. You heard from Parvati earlier about her Monte Carlo simulations. So we start with something similar to give us an idea about the amount of volatiles that might be released from the lander, from Eclipse lander, and then look at modeling efforts from Bill Farrell to get an idea about temporal evolution of those volatiles. Then we use that data as an input to look at molecular simulation model that we have put together for our instrument. And this, the results of this finite element modeling effort has allowed us to fine-tune the design of the instrument, as well as concept of operation. Next slide, please.
If you can, oh, there you go, last slide.
Yeah,
you can wrap it up in a minute, that'd be great. Thank you.
So in summary, this is a really low swap, simple instrument that can detect gases and volatiles with very high sensitivity and selectivity. We can deploy it in a variety of mission architectures, including atmospheric probes, landed missions, or even as a network of sensors to perform new science. And I'll just leave it at that. If anyone has any questions or thoughts, please feel free to reach out to me. Sorry about the technical difficulty.